In this talk, I'm going to summarize the finding of the SIGTYP 2024 shared task on word embedding evaluation for ancient and historical languages, organized by myself and my colleagues Adrian, Priya, Atul, Pádraic and John. In recent years, sets of downstream tasks called benchmarks have become a very popular, if not default, method to evaluate general-purpose word and sentence embeddings. Despite the general trend towards multilinguality and ever-growing attention to under-resourced languages, ancient and historical languages remain undisturbed by such benchmarks, and the goal of this shared task was to bridge this gap. The shared task involved 3 problems for 13 ancient and historical languages in the constrained setting and 5 problems for 16 languages in the unconstrained setting. These languages belong to 4 language families and use 6 different scripts. There were 14 registrations in total and 3 submissions to each track, with 2 successful submissions to each track, which resulted in 4 system description papers. You can see a few important links on the slide. The first link is the shared task GitHub. Then we have the list of text sources for the dataset. Then the links to both constrained and unconstrained tracks on CodaLab, and finally the final version, the updated version of the dataset with the test labels on Zenodo. The original version of the dataset, as participants saw it, is available on GitHub. As I said before, there were 2 subtasks or 2 tracks, constrained and unconstrained. The constrained track included part of speech tagging, morphological feature prediction and lemmatisation, and the unconstrained track included all these and also fill in the gaps or mask filling on word level and character level. The data for problems 1 to 3 comes from Universal Dependencies version 2.12, which was the latest version at the time we created the dataset. For 11 ancient and historical languages, we emitted corpora which contained fewer than 1,000 tokens or for which only a test set was available. All Hungarian texts annotated to the same standard as UD corpora were added to the dataset from the Hungarian Generative Diachronic Syntax website. Historical forms of Irish were only included in mask fill-in challenges, and the quantity of historical Irish text data, which has been tokenized and annotated to a single standard so far, is insufficient for morphological analysis tasks. The Irish texts were drawn from Corpus of Electronic Texts, or CELT, the Historical Irish Corpus, and from digital editions of the St. Gall Prussian glosses and the Würzburg Irish glosses. The table gives an overview of the dataset. The first column is language, where card symbols indicate language families. Club means Indo-European, diamond Afro-Asiatic, spade Sino-Tibetan, and heart Finno-Ugric. The code column refers to an ISO 6393 code with the exception of medieval Latin. We manually split Latin data into classical and late Latin and medieval Latin, and this split was dictated by the composition of the source tree banks. The script column refers to the scripts used in the dataset rather than the scripts typical for a particular language. As you can see, our Vedic Sanskrit data is transliterated into Latin. The dating column describes the period when texts in the dataset were created, set it according to the electronic editions or corpora these texts come from. The apotemporal boundary was set to 1700 Common Era, and texts created later than this date were not included in the dataset. The choice of this date is driven by the fact that most of the historical language data used in word embedding research dates back to the 18th century CE or later, and we would like to focus on the more challenging and yet unaddressed data. Finally, we provide the size of each subset in sentences and tokens. As it is common in evaluation benchmarks, we use multiple metrics for every problem except for morphological annotation. This helps to smooth out shortcomings that individual metrics may have and to make the evaluation scenario more forgiving for complicated problems. Thus, we used accuracy at 1 and F measure for part of speech tagging, and a combination of accuracy at 1 and accuracy at 3 for lemmatisation, filling the gaps at word level and filling the gaps at character level. In the case of morphological annotation, we calculate a macro average of accuracy at 1 per tag and also introduce punishment for predicting incorrect features. We provided baselines only for problems 1 to 3, and the baseline was a simple multi-layer perceptron architecture with no pre-training, which means that embeddings were trained at the first layer. We trained individual models for each language for part-of-speech tagging and lemmatisation, and language-agnostic models for each of the 44 morphological features. You can also see a few hyperparameters common for all models on the slide. For the constrained subtask, participants were not allowed to use anything apart from the provided datasets, but they could reduce and balance them if they saw fit. Our intention was to avoid any cross-lingual transfer in the constraint setting, including the transfer between languages within the provided dataset. However, we seem to have failed to communicate this properly, and one of the systems submitted to this track made use of cross-lingual transfer within the dataset. Nevertheless, the system with embeddings pre-trained for each language individually achieved a better result. So the winning team in the constraint track represented Heidelberg University and Sattler College, pre-trained contextual, word and character embeddings from scratch for each language in the dataset. They used hierarchical tokenization and Berta version 3 for part-of-speech tagging and morphological feature prediction, and character level nano T5 for lemmatisation. These architectures made them on par with the winners of the unconstrained track. The team representing Allen Institute for Artificial Intelligence pre-trained a multilingual transformer model, Libertas, that follows Roberta pre-training architecture. The authors point out that their model struggles with multi-word expressions in Coptic and Ancient Hebrew, which most likely refers to composite characters and vowel markings. Despite the use of cross-lingual transfer, the model's average score falls about 10% behind the winning team. For the unconstrained subtask, participants could use any additional data in any language, including pre-trained embeddings and large language models. The winner of the unconstrained track is the SIGTYP team that used their own parser for problems 1 to 3. They used it with openly available contextualized embeddings such as multilingual BERT, XLM Roberta, GPT-2, and language-specific varieties of these, such as Hebrew BERT or Slavic BERT. The team used distilled BERT for word-level mask filling, and, surprisingly, an embedding-less n-gram model for character-level mask filling. The Tartu NLP team from the University of Tartu applied the same approach uniformly to all tasks and all 16 languages. This approach was fine-tuning stacked language and task-specific adapters for XLM Roberta. Although their system is outperformed by UDParse, this is probably explained by the effectiveness of the UDParse morphological parser rather than by the quality of embeddings employed by either team. At the same time, Tartu NLP outperforms UDParse in lemmatisation and word-level mask filling. The team's results for character-level mask filling generally concede 10 to 15% to the winner, which highlights an interesting observation. A very simple character n-gram model used by UDParse can be more effective in low-resource setting than cutting-edge approaches. This table shows the results for problems 1 to 3 for both constrained and unconstrained tracks and compares them to baselines. The winner of each track is marked in bold and the overall best result is underlined. The team names are as provided by participants except HDB POS, which stands for Heidelberg Boston. The top table shows the results for problem 4. The winner is marked in bold and the absolute best result across all languages is underlined. The bottom table shows overall results averaged across all problems for a given language. The winner for each setting, constrained or unconstrained, is marked in bold. Now, some observations. All participants leveraged various transformer architectures, with Roberta and its modifications being the most popular one. While all participants outperformed our baselines for morphological feature prediction, with best average results about 96% across 13 languages, only the winning teams beat the baselines for part-of-speech tagging and lemmatisation. Baselines were not provided for the mask filling problems, which formed part of the unconstrained track only. At the word level, the winning team could not achieve a higher average accuracy across all 16 languages than 5.95%, with the best result for an individual language being 16.9 for medieval Icelandic. This outlines the particular difficulty of this problem. At the character level, the best average result over 16 languages was 55.62, and the best result for an individual language was 74.59 for Gothic. Data scarcity influences sequence labeling tasks, such as part of speech tagging and morphological feature prediction, but this effect is not as dramatic as one might expect. Thus, the difference between the smallest corpus of 21,000 tokens and the biggest corpus of 599,000 tokens is only 9.5 on average across all submissions for part of speech tagging, and 11.3 for morphological feature prediction. The same is true for lemmatisation. However, models trained for this task seem to be more susceptible to orthographic variation and lexical variety in the data, as well as to the morphological complexity of a language. Thus, we see poorer results for lemmatisation across all languages, despite the milder metrics. Cross-lingual and cross-temporal transfer could have played an important role in the systems that used XLM Roberta. However, similar results can be achieved with pre-training on modestly sized monolingual data without any transfer, as the winners of the constrained track showed. Mask filling tasks appear to be much harder than we expected even for state-of-the-art models. The problem could be attributable to the following reasons or to some combinations of them: high lexical variety, orthographic variation, relatively short sentences, code switching, for example Latin in historical Irish texts, data scarcity. As we know, mask filling requires more training data than, for example, part of speech tagging, composite characters and vowel markings in Coptic and ancient Hebrew, not trivial character decomposition in classical Chinese. So, the shared task was an important step towards creating a universal multilingual evaluation benchmark for embeddings learned from ancient and historical language data. The dataset and evaluation scripts are available on our GitHub and Zenodo, and the post-competition phase and Codalab will remain open for anyone interested in testing their approach on our data. We're planning to further expand the dataset with more languages and add more downstream tasks in the next release of the benchmark, and we would certainly appreciate any advice and collaboration from both computer scientists and historical linguists. Thank you for your attention, and if you have any questions, my email is on the slide.